We're going to be talking about the ingredients needed for severe storms to occur and produce those hazards that we're looking for: large hail, damaging winds, and tornadoes. And perhaps the most important of these ingredients is moisture. All of these ingredients we'll be talking about today are important, but moisture is perhaps the most important because without adequate moisture, it's hard to even get robust storms, let alone robust severe storms. So moisture is very important. And in the context of severe storms forecasting, when we're talking about moisture, we're referring usually to a quantity called the dew point. Many of you have probably heard of the dew point before. The dew point is simply the temperature to which the air must cool in order for dew to form, as the name suggests. In more technical terms, it's the temperature to which air must cool in order for condensation to occur, or in order for the air to become what we call saturated. So basically, saturated means that the air is holding as much moisture as it can possibly hold, and that's what the dew point represents.
Storm chasing is hard. Get expert help from a live coach. Discord community link in description.
So for example, let's say we have a surface temperature of 75 degrees Fahrenheit, and in this given environment, our dew point, let's say, is 50 degrees Fahrenheit. That means that our air temperature at the surface would have to cool from 75 degrees Fahrenheit all the way down to 50 degrees Fahrenheit in order to become saturated. At that point, surfaces that are at that temperature, that 50-degree temperature, would start to have condensation, water droplets condensing onto them. And if you're at the surface and the temperature reaches that dew point, oftentimes you will see fog, because that's when the air is saturated and that water vapor that's in the air is condensing into actual water droplets to form clouds, or at the surface, it's fog. In severe weather situations, we typically want the dew point to be on the higher side, at least relative to the temperature. So let's say we have a temperature, again, of 75 degrees Fahrenheit. Our air temperature at the surface is 75 degrees Fahrenheit, but our dew point is 40 degrees Fahrenheit. That means that air is going to have to cool all the way down to 40 degrees to become saturated. That indicates a fairly dry atmosphere. One of the basic tenets of meteorology is that warmer air holds more moisture. So in this case, even though if we were to cool down this air temperature at the surface down to 40 degrees, the actual amount of water vapor in the air is not changing. But because this air, we have to cool this air all the way down to 40 degrees Fahrenheit to get to that point of saturation, that indicates as a much cooler temperature, of course, and it technically doesn't hold, quote unquote, as much moisture as, let's say, a dew point of 65 degrees Fahrenheit. So let's say that same scenario, we have 75 degrees surface temperature and a dew point of 65 degrees Fahrenheit. Now, we don't have to cool that air all that much down to 65 degrees Fahrenheit to get to that point of saturation and to reach the dew point. That indicates a much more moist environment than this environment on the left here. Generally, we want our dew points to be on the higher side for severe weather, especially relative to our temperature. Because let's say if we have a dew point, let's say our dew point is 75 degrees Fahrenheit. That at the surface just by itself is a pretty high dew point. But if we have a temperature of, say, 105 degrees Fahrenheit, our air temperature at the surface is 105 degrees Fahrenheit, that's still quite a ways we have to drop to get to that point of saturation, and that's still generally a relatively dry environment. But let's say if we have a dew point of 75 and our temperature is, let's say, 82 degrees Fahrenheit, that's a much more moist environment because that temperature, that spread between the temperature and the dew point is not that large. And for tornadoes to occur, we want that temperature dew point spread, as we call it, to be on the lower side, generally within about 20 degrees Fahrenheit or so. Now, just a quick note, the dew point can never be greater than the air temperature. So if you have an air temperature of 75 degrees Fahrenheit, your dew point can never be, say, 80 degrees Fahrenheit. That's just not possible. There are some very special situations in the atmosphere where this can happen briefly, but for most purposes, and really all purposes within severe storms forecasting, you will never see the dew point be greater than the air temperature. Our typical ranges for severe weather, as far as the dew point goes, most of the time you want to see those dew points in the 60s Fahrenheit. That typically is rough rule of thumb. Again, it varies based on the air temperature and some other factors in the environment. There's been severe weather setups that have happened with dew points in the 40s and 50s, but usually this is when your air temperatures are in the 50s and 60s, so that temperature dew point spread is on the lower side. This happens a lot in the fall and winter months when simply the air temperatures are often cooler, they don't hold as much moisture, so you don't need as much moisture in those off-season setups than you do in, say, the spring, when our moisture return is more robust and our air temperature is greater overall. It's all dependent on, and it's all relative to the air temperature. But most of the time, for most of your robust severe weather events, those dew points really need to be up in the 60s, particularly above about 65 degrees Fahrenheit or so, mid to upper 60s into the 70s, to really have robust moisture, especially at the surface. When we're talking about all of this, we're talking really focusing on the surface, but moisture is important as you go up in the atmosphere as well. But for the surface, that dew point needs to be relatively high relative to the temperature, and in most cases, for most robust severe weather events and tornado outbreaks, you want that dew point up into the mid to upper 60s, even into the 70s. Another caveat to this is also elevation. Air at higher elevation does not hold as much moisture as air at lower elevation. So if we have, let's say, the same dew point at Oklahoma City as we do at Denver, let's say we have a dew point of 60 degrees Fahrenheit at both of those locations. That 60-degree dew point is going to be a lot different at Denver than it is at Oklahoma City, because Denver, that air is at much higher elevation, so it doesn't hold as much moisture by nature. So the fact that you have a 60-degree dew point indicates a very moist air mass, perhaps a much more moist air mass relative to what the air mass would be at Oklahoma City, which is at a much lower elevation. So oftentimes in the higher elevation areas, severe weather can happen with much lower dew points than the same setup at a lower elevation area, say the southern plains. Now, where do these higher dew points come from? Typically, for most severe weather events in the plains or the Midwest or Southeast or Mid-South, it's going to come from the Gulf. That air above the Gulf is fairly high in moisture content. Those dew points are usually fairly high in that air mass over the Gulf. As these severe weather events get going, the winds in the low levels can start transporting the air that's over the Gulf that holds those higher dew points up into the inland areas of the U.S., again, the plains, Midwest, Mid-South, Southeast. And that's really our major moisture source for where these higher dew points come from. You can have some exceptions. Basically, if you're in the, say, Pacific Northwest, you'll get some of that moisture off of the Pacific Ocean. If you have Atlantic severe weather events, you can get, oftentimes the Gulf moisture will be our main moisture source, but you can get some enhancement from the moisture off of the Atlantic. But for the majority of severe weather events in the central U.S. corridor, that moisture is going to come from the Gulf down to our south. That's our main moisture source region for those higher dew points for most severe weather events in the U.S. Our next severe weather ingredient is instability, and instability is basically the ability of air to rise on its own. And this comes from another basic tenet of meteorology that states that warmer air tends to rise while colder air tends to sink. And so the way we can build instability in a given environment is to warm up the air at the surface to make it warmer than its surroundings. And when the air is warmer than its surroundings, it will have a tendency to be able to rise on its own. There are a number of ways we can actually achieve this. The first is through the sun. When the sun is shining on the morning or afternoon of a severe weather event, that allows the air at the surface to warm and warm to a point at which it becomes warmer than the surrounding environment, and then it can rise on its own. The second way to do this is to transport warmer air into a region from elsewhere. So in our previous section on moisture, we talked about how that air mass that sits over the Gulf is consistent with higher dew points. That air mass is also a lot warmer. So ahead of these severe weather events, as that air mass gets transported inland into the United States, that air mass is much warmer and more moist than the air that was basically sitting there over the plains or wherever previously. So that allows the low levels in the air near the surface to warm up, become warmer than the surroundings, and be able to rise on its own as well. The third way we can achieve this is to transport colder air aloft. So the middle portion and the upper portion of the atmosphere, we can transport colder air from another region into a given region. That allows instability to build as well, because we can assume that it stays the same temperature, But if you make the air just above that colder, that allows the air at the surface to be warmer than the environment and rise on its own. We keep talking about the surface, but really this does apply to the entire atmosphere. We want the air at every level of the atmosphere to be able to rise on its own, or air from the surface to continue to rise on its own throughout the entire atmosphere. That means that the atmosphere is fully unstable, which can allow for storms to really tap into the environment in full and become their most robust. So those are really the main mechanisms that allow us to build instability in a given environment. And oftentimes in many severe weather setups, you'll see many of these mechanisms occurring at once, and that allows instability to build and build over a period of time during a given day for the environment and storms to act upon that instability later on in the day. Our main measure of instability is called CAPE, which stands for Convective Available Potential Energy. We won't go too deep into how this is calculated in this series. We'll talk a little bit about that in the next episode as well. But CAPE is our main measure of instability, and the more CAPE you have, the more unstable the environment is. And just for some general guidelines, severe weather events can operate with CAPE on the order of 200, 300, 400, 500 joules per kilogram. CAPE is a measure of energy per unit mass, so joules per kilogram. Again, don't worry about that too much, just focus on the values here. But instability is certainly an important ingredient, but severe weather events can happen with somewhat more limited CAPE. Generally, you see CAPE values of about 1,000, 1,500, 2,000 joules per kilogram. Anything above 2,500 joules per kilogram is considered strong instability. Anything over 4,000 joules per kilogram is considered extreme instability. Now, the amount of CAPE does not directly correlate to tornado production. What it does correlate to is updraft strength. So the more CAPE you have, the stronger and more robust updrafts can be. The faster that air can move upward within the updrafts. And that leads to more robust storms and perhaps more severe storms in certain cases. But it does not correlate directly to tornado frequency or tornado production in storms. There have been many events with really extreme instability that have not produced tornadic activity, and there have been events with pretty low CAPE values that have produced significant tornadoes. So it's not directly tied to tornado frequency or production. We're going to talk about the variable that really does correlate to that and really does modulate tornado production here in just a second. Of course, you do need some instability to support robust updrafts, which can become full-fledged storms and severe storms that can therefore produce tornadoes in the long run. Our next ingredient goes hand in hand with instability, and it's called lift. As we talked about just earlier, instability is the ability for air to rise on its own. And that's all well and good. Instability is a necessity for severe storms to happen. But the air that's near the surface needs a little bit of a push upward to be able to rise on its own. Just like if you were to sit on a swing at a playground. If you were to just sit on that swing, you're not going to swing back and forth. You actually need to give yourself some momentum, back up a few steps, and propel yourself forward to allow yourself to start swinging back and forth. The same thing happens in the atmosphere. That air in the low levels is just sitting there. The atmosphere can be unstable. You can have all the instability you want, but if you don't have a mechanism to propel that air upward or lift that air upward, then you are not going to be able to initiate severe thunderstorms. There are many different lifting mechanisms that severe weather events can have. Perhaps the most prominent is a trough. A trough is basically just a big storm system. We're going to talk about troughs a bit more in our next episode, but those troughs are perhaps the most common lifting mechanism or forcing mechanism. If you hear me use the word forcing, those are interchangeable. It means the same thing. You're lifting air up, you're forcing air upward so that it can tap into that instability. Those are used interchangeably. So you can have big troughs. You can also have surface lows, areas of low pressure at the surface. Those are associated with frontal zones, cold fronts, warm fronts. Those can be lifting mechanisms themselves. Same thing with the surface low. The surface low provides a little bit of extra forcing or lifting associated with it alone, and then you have the forcing along the boundaries as well. Another common one is topography. Big mountains, mountain ranges, big terrain features like ridges or plateaus. Those can help lift air upward. Air can't go through these big mountain ranges, so what happens is it gets forced upward or lifted upward, and that's how you can attain rising motion by topographical features. These are just a few of the lifting mechanisms that can occur in severe weather events. There are many others, but these are perhaps the most common. So these first three ingredients that we've discussed, moisture, instability, and lift, those are required for just general thunderstorms. All thunderstorms need moisture, instability, and lift to survive. What makes storms severe is an ingredient called wind shear. Wind shear is the change in wind speed and direction as you go up into the atmosphere. As you might surmise from that definition, wind shear can be broken up into two different parts. Speed shear, which is the change in wind speed as you go up in the atmosphere. So if you have winds that are, say, at 10 miles per hour at the surface, but in the upper levels of the atmosphere they're 100 miles per hour, that is strong speed shear. And directional shear, which is the change in wind direction as you go up in the atmosphere. Let's say we have winds that are out of the southeast at the surface, but our winds in the upper levels of the atmosphere are out of the west. That is strong directional shear. Both of these are equally important in making storms severe. Speed shear helps to tilt the updraft. Every thunderstorm consists of an updraft, which is the warm, moist air that gets sucked into the thunderstorm, and a downdraft, which is the rain and precipitation and the air that accompanies that precipitation as it descends toward the ground. So if you are familiar with just general summertime thunderstorms, you probably see that the storm is pretty much straight up and down with no real tilt to the thunderstorm cloud, and the precipitation or the rain is falling directly underneath the base of the updraft. This is a typical summertime thunderstorm, and these don't last very long. That's because the rain-cooled air in the precipitation core is interfering with the warm, moist air that's being sucked up by the updraft. So that allows the storm to really not last all that long. These are more pulse-type thunderstorms. They pulse up real quick, and then they fall apart because of that coincidence between the rain-cooled air in the downdraft, which is that precipitation core, and the warm, moist air in the updraft. Speed shear helps to tilt the updraft so that the rain-cooled downdraft, that precipitation, is displaced from the actual updraft. That allows an uninhibited flow of warm, moist air to come into the updraft without that rain-cooled air cutting it off. So that's why speed shear is important in severe storm formation. It tilts the updraft, displaces the downdraft from the updraft, and allows the storm to live a lot longer. Directional shear is important because it allows the storm to rotate, and rotating thunderstorms can produce those severe hazards like large hail and tornadoes. Those are storms that are called supercells. Supercells have an updraft that rotates, and that is due to directional shear. So speed shear and directional shear, both are important. To have both in an environment is optimal. You can have one and not the other and still have severe storms, but optimally, we're looking for wind shear in the form of speed shear and directional shear in the environment. For supercells to produce tornadoes, we want to see strong low-level wind shear, which means the winds are changing abruptly in direction and strengthening in intensity in those lowest levels of the atmosphere, really the lowest kilometer or so just above the surface.
Remember to check out those links in the description below, and then watch another video.